Computer scientists often analyze algorithms as a indicator of what's going to be the most promising, the most efficient, the most effective, or just simply comparing the different algorithms that might solve a particular problem. It's important that we understand right up front the difference between estimation versus approximation here. Um, Empirical evidence here is the best indicator of real world phenomena. So, we can do that by, in this case, calipers or measuring or whatever, by running code and seeing what the actual outcome is. But there's a lot of variations when you go and run code. What computer you're running on, what other things were running in the background, how well the algorithm was actually implemented, what the nature of the language operating system or other, there's a lot of variances that can go inside of there. So computer scientists often use mathematical approximation, like our little jar here. How many candy corns is in the jar? Well, you could easily open it up and count them. That's not the end of the world, but by approximating it, it gives you a good feel of where it's going. It takes a heck of a lot less effort in order to be able to get there. That's the main value of approximation. So if I want to, for instance, know which of these planes is the most efficient in flying, use the least amount of gas or can go the fastest or whatever the question is, I can put it in a wind tunnel and get an approximation of what that full plane might do. I don't want to go build a many million dollar or tens of million dollars or hundreds of million-dollar craft just to figure out if that design is optimal or not, if there was a better design. But even in this case, the wind tunnel model often has tens of thousands of dollars of effort put inside of it. So the difference in what we've done a little bit of in class of building a bunch of algorithms and then comparing them empirically versus approximation is it saves you the time of having to build something. We can just straight do the math and predict in its purest, cleanest form how fast should this algorithm perform, especially in comparison to other algorithms. So there always could be variations, there always could be differences, and there's often going to be other trade-offs that we'll talk about here in some of the examples through the sequence. But it is important to get this idea that approximation is a very important tool to consider ahead of time and not just necessarily building both things and going with it. It's one thing when you're building a sorting algorithm, it takes you like an hour to go off and build it. But if you have a whole team of people that might be spending, days, weeks, months to go build one option, I don't want to do that a second time. I want to have a good feel ahead of time. So as we estimate performance, typically there's some basic scales we can talk about it, where we have something like the constant performance. So we used array lists, and the great thing about an array list is whether I'm accessing the first element on the list or the 10th element on the list or the 10,000th element on the list, it's a constant return time. It's just quite literally math. When I say return storage of 10 or 100 or a million, um, all we have to do is take that number, multiply it by the data size, add that to the initial address of the array, and so multiplication, addition, done. We have it. It's a constant time. It doesn't matter. It's just a matter of the scale of the numbers. It doesn't take a lot longer to multiply a million than it does to multiply by 10, right? As opposed to a linear way of solving that, which would be like a linked list, where I have to go through each node on the list. So if I'm going through 10, my time is 10. If I'm going through 1,000, my time is 1,000. Potentially. It could be faster than that. If I'm looking for the first element of the list, it's quicker. But the worst case scenario is going to be the size of the list. I look through every element once. There are some algorithms, though, we can't do it either constant or linear. We have to look through many things. So if I want to, for instance, sort the list, many of the algorithms we've talked about so far have quadratic times that are going inside of there. So for each value on the list, we're going to look at every other value on the list, and if it's smaller, we swap it. So essentially, anytime we get into nested lists, a for loop over a for loop, we risk being, not always are, but we risk being quadratic, or worse, we have cubed inside of there, or more. So it depends on the nature of the algorithm and the way we do that. And there's actually other mechanisms that we can talk about inside of here, we're going to talk about in a second, that are somewhere in between. We generally don't make algorithms that are worse than quadratic, though, because as we're going to see, their complexity and thus their time explodes massively. But sometimes we do have fairly inefficient algorithms overall because in computing, scale matters big time. So this is a picture of a time-elapsed picture of a car racing a human. And you'd say, well, if a car races a human, the car is going to win every time. And that's true of any scale over about 30 meters. But if you get a world-class athlete, an Olympic sprinter, from 0 feet or 0 meters to 30 meters, 0 feet to 150, to about 90 feet, a human accelerates faster than a car. A car has a heck of a lot more to get going here. And so if you're saying the race is 100 meters, a car is going to win every time. But if you're saying the race is 20 meters, a human might win in many cases. A human might beat them to that finish line in a whole lot of times. So if you have a problem that's only ever going to store 50 items, it might not matter exactly how efficient your algorithm is. Or there might be algorithms that would be inefficient later, but might be very efficient in that short amount of data. So we got to think about that when we look at some of our algorithmic choices. So in small data, we can see here we have linear as the light blue here down in the middle, and then we have linear log and versus logarithmic and constant. Now, you can't really see constant. I mean, constant's going to be what it is. It's going to be tiny in this scale. This is going up to 2,000, but we can see if we have x squared, a quadratic equation, it jumps up pretty quickly. So even after 30 cycles, this one is up to over the 800 time, if you will. Not exactly what we're talking about, but jump up quickly. Or cubed goes up really, really crazy. But what we want to try and do is live in this space of linear and linear logarithmic, or just even better, just straight logarithmic responses to things. Because as time spreads out, they do start to show a little bit of a difference. Linear equations are much better than linear logarithmic equations. And logarithmic equations themselves remain insanely low until you get to really, really high numbers. And that's where we can talk about some of the analysis of algorithms and how we come up to this. But we're introducing this idea of logarithms, and I don't know if you remember what they are from math classes. So let's talk about the mathematical power of logarithms. So let's just say we have a lonely mama bunny who comes pouncing in the field. And so we have one bunny. And so she has her babies, and she has twins. And so now we have three bunnies. And then each of her babies then also goes off and has twins. And now we have seven bunnies. And so, 3 generations later, was it seven bunnies? That's not so bad. I mean, if you had this in a cage, you'd be like, oh, okay, well, that's a lot of bunnies. We're done having bunnies now, but it's not overwhelming. But if all of these rabbits again go off and have another set of twins, then all of a sudden, we're starting to have a lot. Now we have 21 bunnies. And if we allow that to happen again, well, oh my. I mean, they just start coming on top of that. So the bunnies just keep coming and coming and coming. So at this point, one, two, three, four, 5 generations later, we're into like 100 bunnies. That's the power of exponential growth. But logarithms is not counting the individual growth. Logarithms is just paying attention and segmenting it down by just that generation. So we can talk it as 2 to the 0 is 1, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, a truly exponential growth in powers of 2 in this case. But if we look at that, we're counting that as really actually being 0, 1, 2, 3, 4, 5 if we count the generations. And so if we can have some way of ignoring the exponential growth of data and instead focus on the scaling. So, if we talk about that population growth, if we map this out, this is what it looks like. So generation 0 is a few, and 2, 3, 4, 5. It's this is a huge scaling. But by the time we get to generation 8, you're talking more than 2,000 of these bunnies growing up. 9 over 6,000. 10, you're getting close to 20,000. This is a huge amount of data, a huge amount of bunnies out there that are growing. That's why invasive species can be so dangerous when they're left unchecked. They can really grow if there's no natural predators or whatnot. They can really take over in just a few generations. But if we look at this at a logarithmic scale, and instead of looking at this as 1, 2, 3, 4, 5, 6, all the way up to 20,000, if we look a logarithmic scale, we look at this as 1, 10, 100, 1,000, 10,000, and just map it that way. All of a sudden, this looks linear because logarithms allow us to grow high numbers, but just looking at essentially the powers that's going on inside of there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gives us this growth. And so the bunnies here grow each day, each generation, however you want to look at it. It's linear. It's linear growth on a logarithmic scale. So it's like, okay, well, yeah, but what does that mean to algorithms? Well, we can harness the logarithmic power by creating data structures and algorithms that split data generationally. So we talked about heaps, and heaps are a form of tree, and at some point, either already or in the future or wherever you're watching this video, you'll learn about trees as well. But the idea of the full tree is you have this logarithmic power where you start with some number and then you split it in half. And so in a normal binary search tree, your lower values go to the left and your upper values go to the right. In a heap tree, you're always higher than or lower than your other values, but I don't necessarily care, what the order of them is. I only care about higher and lower, but I can still essentially get to all of my values logarithmically. So if you remember the height of a tree here, so this is up here, level 0, level 1, level 2, level 3. So this tree has 4 levels, and it stores 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, potentially 13, 14, 15. So it stores 15 values in 4 levels. Well, we add a 5th level, all of a sudden it stores 30, 31 values, 32 values. At a 6th level, and now it's all of a sudden storing 64 values. So again, with the number 6, we've now stored 10 times that in values. Well, we add number 7, well, that's 128 values. That's way more than 10 times that. But now we also have a way of searching those. So we put in a binary search tree, we put it at the end. At most, we have to bubble it up 5 times at that point, or 6 times, or 7 times. But every level we add, we're doubling the amount of storage we have, yet we can still figure out which is the smallest or largest value in 7 or 8 operations. And so what we're going to see is algorithmically, we want to try and find analysis of algorithms, and we use our analysis of algorithms to define and create and use algorithms that take advantage of logarithms. So what we're going to look through in this section is these tools of analysis and what it means, and how do we figure out if an algorithm is taking advantage of logarithmic powers or not, or if it's quadratic, or if it's worse than quadratic. And that'll help lead us to choosing algorithms that are best for our situations. Again, there's other factors than just speed. We have to figure memory, we have to figure complexity, we have to figure scale, but the analysis lets us have the data to be able to compare the things before we get into those discussions. And that's what we'll look at here in the next few videos.